In our last video, we did an introduction to momentum and the topic of conservation of momentum. How do we put momentum into a system or take momentum out of a system by using impulse? But even in that video, I was starting to hint at the topic of collisions. So in last week's unit on energy, we found that we could use conservation of mechanical energy to do a lot of different problems. But we had to distinguish between conservation of energy and conservation of mechanical energy, because energy can be required to do all kinds of things, like make noise, make heat, crumple different objects, and we didn't know how to account for that. What we find now is this topic of momentum is built on Newton's laws fundamentally. So if Newton's laws are always true, this topic of momentum is probably going to be more useful, because conservation of momentum is always true, and momentum doesn't take a variety of different forms. Momentum's just momentum of the system. And so it turns out that if we happen to have some objects interacting where we expect some of the energy to do other things that aren't mechanical, such as crumpling a bumper, making noise, making heat, making light, any of these things, momentum is going to be a much more useful way to think about it. And so as we get started here inside of OneNote, there are a variety of different collisions that we could look at. One of them is a perfectly inelastic collision, shown over here on the right in red. This is a type of collision where one object hits another object. Okay? So something's rolling along, it hits another object, and these two objects become one new object. Now we might think to ourselves, well, we could do this maybe by firing a bullet into a block of wood. That is two masses becoming one mass. Or we could throw a piece of Play-Doh at a block, and these two masses become one mass. But it doesn't have to be so destructive as that. We don't have to bore a hole into the other object. We don't have to completely squish the Play-Doh mass or clay or whatnot into the other mass. Sometimes this is just as simple as two train cars with hitches connecting. And that's really also a case of two masses becoming one mass in that scenario. Now, some of these changes are going to be irreversible. If you were to fire a bullet into a block of wood, that block of wood is irreversibly changed. The bullet is irreversibly changed by changing shape. Maybe it gets hot. A lot of different things happen. And so energy that was originally in that bullet has to go off and do other things. Energy is no longer, at least mechanical energy, is no longer conserved. But momentum in that system is. Okay, well, what's the other extreme scenario? Not every collision is going to have all this destructive behavior. Obviously, there are some situations where conservation of mechanical energy is also going to hold. And that's the other case over here on the left in green, the perfectly elastic collision. In this scenario, not only is conservation of momentum something that holds because it holds all the time, but conservation of mechanical energy holds as well. All the kinetic energy that we had in the system at the start is kinetic energy that we have in the system afterwards. And so, energy is maybe sloshing around, but none of it is turning into sound, none of it is turning into heat, none of it is turning into an irreversible change of some object. And in reality, none of the collisions that we really work with are likely these two extremes. So a perfectly inelastic, that's pretty easy to figure out. Two masses becoming one mass, but maybe some part of it as it's being deformed comes off. Okay, fine. Or in the case of a perfectly elastic collision, maybe there is just a small amount of noise or a small amount of heat or vibration that's made. But most collisions are going to be somewhere in the middle. In each of these scenarios, you notice that momentum is conserved for a perfectly elastic collision, momentum is conserved for a perfectly inelastic collision, and momentum is conserved for every type of collision in between. Conservation of momentum is something that holds all the time. Whereas in some of these cases, mechanical energy can be conserved. Some of these cases, mechanical energy is certainly not conserved, and sometimes mechanical energy is somewhat conserved, but not completely. And so I'd like to look at each of these scenarios individually. And to start with, let's look at the case of the perfectly inelastic collision, the one that's in red here. Because while you'd think, well, perfectly inelastic collision, that seems like the hard place to start. It's the easiest possible scenario because we have two masses coming together to become one new mass. So if we look at the momentum at some initial time before there was a collision and the momentum at some later time after the collision, those two momentas have to be the same. So initially we might have m1 moving at some initial velocity, m2 moving at some different initial velocity, but we can figure out what that total momentum is. m1 v1 initial plus m2 v2 initial. And if we have conservation of momentum that holds, the system remains closed and we're not doing any impulse. The only impulse that's happening is between the two things that are interacting. That's what it means to have a closed system. Then after that collision, when the two objects become one object, they have some final velocity. We could find what the final velocity of that system is after the collision. Or using this kind of a relationship, if we knew one of the masses before the collision and what the velocities were of all the scenarios beforehand, we could find a missing mass. Or algebraically, this is some setup that looks at a simple scenario. So looking at this expression, if we had two masses that were identical, m1 and m2 were the same, if they were heading directly towards each other at the same speed, opposite directions, so they're opposite velocities, we see that the final velocity when the two objects become one object is going to be equal to 0. Or similarly, if we had one object hitting another object, maybe m2 was initially at rest, which means this goes to 0, v1's coming in at, 10 meters per second or so, but if m1 and m2 are the same, the final velocity of the final object, when they become now one new object, is now going to be half of what it was before. So perfectly inelastic collisions are a special case when two objects collide and become one new object. Maybe they get bumpers that are connected together. Maybe it's train hitches that are connected together. Maybe it is a bullet wedged in a block that wasn't before. But these are the case of perfectly inelastic collisions. Okay. Now, we're going to look at some examples of perfectly elastic collisions just a little bit later when we're doing some problems, but I want to get definitions out for the types of collisions first. And now we could look at the other extreme scenario, which is the perfectly elastic collision, the case when not only is momentum conserved, but mechanical energy is conserved as well. Nothing is lost to heat, nothing is lost to sound, nothing is lost to any other thing. All changes in the shapes of things are reversible changes. And so in this scenario, if we were to look at conservation of momentum of two objects before the collision and two objects after the collision, m1 v1 initial plus m2 v2 initial, that's the initial momentum, and after the collision, m1 v1 final plus m2 v2 final, okay, conservation of momentum is relatively straightforward. But we could also look at the case of what's going on before the collision in terms of energy, particularly kinetic energy. And we see that 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared, this is some kinetic energy in our system. And after a collision, the velocities of these two things could be different. That's what we implied here with the momentum as well. So we could also have some set of kinetic energy after the collision. Now this all happens instantaneously at the impact of a collision. So do we have to keep track of potential energies and the like? Well, no, not really, because this is all happening instantaneously, right? So it's not like some of our energy is going into energy of height because they happen at a point in space. It happens at one kind of a position. And maybe after a collision, a spring gets compressed, but the collision itself happened in an instant, happened at an instantaneous-ish kind of a place. So while we would think to ourselves that mechanical energies take a lot of different forms, oftentimes what we find is the collision has the conservation of momentum, and then we would do the energetic stuff later on. And we're going to look at a couple of examples of that later. Now, if we're really going to hold to the case that momentum is conserved and mechanical energy is conserved, this is a system of two equations and two unknowns. Maybe we know what the two masses are. Maybe we know what the two initial velocities are. So looking at this scenario, maybe we want to find out what the final velocities are. That's two unknowns, v1 final and v2 final. But because we have two linearly independent relationships, we should be able to solve this system of equations for v1 final and v2 final in terms of the initial velocities. And the answers are found here. Now I put a little box here, and what I would expect you to do in getting ready for quizzes and getting ready for exams is to have these two equations on your note sheet, because these two equations are notoriously difficult to solve on the fly. You don't want to have to come up with this on exam day. You want to be able to just use it. So while you're watching this video, take these two equations and put it on your study sheet for the exams. Put it on your study sheet for the quiz. You need to have it available. You don't have to know how to motivate it and derive it. You need to know how to use it. Okay? And there's a couple of scenarios that I look at here. Say the cases of two different masses, or two masses that are the same, and one of them is initially at rest, and how what goes along and stuff like that. If you are curious about how this is motivated, you could actually go to the page, this page, Solving the Equations, that's in the notes, and it walks you through about where those two equations came from. But you can already see this is a fair amount of work and a little bit of art putting it together. Once again, you do not want to derive this on exam day. You want to be able to use it. So once again, while you're here, write these two equations on your sheet that you're going to be using. Okay. Now, depending upon the type of collision that we are working with, we may or may not have enough equations to solve uniquely. For an elastic collision, momentum and energy are conserved, so we can solve for two unknowns. And they can be any two unknowns. They could be a mass and a velocity, it could be two velocities, it could be two masses, depending upon the stuff that's given to us. In an inelastic collision, we only really can hold hard to conservation of momentum. But that means that other stuff is going to have to be given to us, most likely. One thing to keep in mind through all of this video and all of the examples that we're going to do, momentum is conserved in every collision. In some cases, we may still need other information, but one thing is true. If you are trying to do a collision problem without using conservation of momentum, you are doing it wrong. Okay, you have to use conservation of momentum if you're ever doing something that looks like a collision. Keep that in mind, because it's something that you're going to be graded on when you're doing exams and quiz work. If you're trying to do something that is clearly a collision and you don't have conservation of momentum somewhere in there, you're going to lose points. And you're very likely going to lose a lot of points because it implies that you're doing the problem wrong. Okay? And you might fumble into some correct answers in some way or another. But, if you don't have conservation of momentum, you're just really not doing it right. This is something that has to hold. This is how we talk about the interaction between two objects. The momentum in some system, it could be transferred and moved around in a variety of different ways. So we are going to look at examples of each of these different types of collisions in just a little bit. But before we get there, I want to talk about one other thing. Momentum is a vector quantity, right? Mass times velocity. And while mass is a scalar, velocity is a vector, which means that momentum is a vector and it can have components. So as we go through these different collisions, it doesn't have to apply in just one direction. It turns out that we can have a certain kind of momentum before a collision, and then we can have different kinds of momentum after the collision. But if we didn't initially have y components of momentum, we can't ever have a net momentum with a y component, even after a collision. So in this scenario that you see here, I'm having M1 coming in and hitting M2. M2 is initially at rest, so the only momentum that we have in our system is to the right. Now after this collision, maybe it's two billiard balls or something like that, it turns off the red ball goes off up and to the right, the blue ball goes off down and to the right. But the way those things are moving, the momenta that are associated with these two different balls is still incredibly linked to each other. Because when we started the problem, we only had an x component of momentum. So if our red ball has a y component of momentum, the blue ball after the collision has to have negative that exact same y component of momentum. Right? And they could maybe have different x components of momentum, all other sorts of things can be figured out. But before the collision and after the collision, the momenta have to be the same. And oftentimes this leads to graphical techniques for solving problems. Because let's say we were to take these different momenta. Here is our momentum 1. Here are the momenta after the collisions, going off at weird directions, theta and phi, with respect to the initial direction. And I can take these vectors and I can move them around, because vectors don't have a position. So why don't I just say that the blue ball, or the red ball, going up and to the right after the collision, well, let's just put that vector right here. It's the green vector P1 final. And the blue ball going off at its various direction after the collision, this is the red thing, I'm going to put that vector here, P2 final. Those are the two final momenta, but the initial momentum, P initial, is right here. Conservation of momentum says that this green vector plus this red vector, the two momenta after the collision, have to be equal to the initial momentum. This is just the vector stuff that we did back in Unit 1. It has to be the same. And so we could start to use things like the Pythagorean theorem, or in this case we could use the law of cosines to find out what a missing momentum is going to be. Graphical techniques work just like algebraic techniques in solving different kinds of problems. We're going to look at an example of this as well. So what I'd like to do with the rest of my time in this video is actually look at a couple of different problems and see how we apply conservation of momentum to solving different things. And so let's first look at a problem like the one that is shown here. In this problem we have a car that is going to hit a truck. And what we know in the problem is the initial speed of the car, we know the initial speed of the truck, and we know the final speed of the car after the collision. So we're supposed to find the speed of the truck after the collision. And if we wanted to, we could look at some other things like the change in mechanical energy of the car-truck system. I may or may not do that here. If you're curious about that, you can go and look at the video where I do this more exhaustively that's already posted in Canvas. But in this problem, before the collision happens, we have the car moving along at V of the car initial. And we have the truck moving along at V of the truck initial. Now, after the collision, these two things hit each other, but they don't remain one object. They remain two separate objects. This is not a perfectly inelastic collision. So what we see is we're going to have the mass of the car, V of the car final, plus mass of the truck, times V of the truck final. This is what conservation of momentum means. And a lot of these things we know. We're told the mass of the car, we're told the mass of the truck, we're told the initial velocity of the car and the truck, and we're told the final velocity of the car. The only thing that we don't know is this, and this is the thing that we're trying to find. Now, oftentimes in one dimension, velocities are going to carry a sign. A velocity that's to the right is positive, a velocity to the left is negative. So in this problem, everything is originally moving to the east, and after the collision, the car is moving to the east as well. So if we wanted to solve this for V of the truck final, I see that mass of the truck times v of the truck final, which is this term, is mass of the car, v of the car initial, minus mass of the car, v of the car final, plus mass of the truck, v of the truck initial. Now, mass of the car is in both of those terms, so I can factor it out. And here we see a change in velocity. This isn't exactly change in velocity because it's not v final minus v initial, but we see a difference in two velocities. Now, we know that before the collision and after the collision, the car is moving to the right, easterly. So both of these are positive, and we're looking at a difference in these velocities. So maybe it's 10 minus 8, which is 2, or something along those lines. But velocity really does carry a sign. If we had been told that the velocity of the car after the collision was 18 meters per second to the west, this would have had a negative sign coded in. We could have had something like 20 minus negative 18, which is 38. So having a velocity that changes direction can drastically increase what something like this term looks like. Now, we don't have that here, and that's fine. But essentially, what we're finding is that v of the truck final is m of the car, v of the car initial, v of the car final, m of the truck, v of the truck initial, divided by the mass of the truck. Now, we could also rearrange terms here just a little bit, and why don't we do that? And what we see is the final velocity of the truck is basically the initial velocity of the truck plus stuff that happens during collision. And very likely, the speed of the car after this collision is going to be smaller than the speed of the truck after the collision, right? In fact, in the text of our problem, the car was originally going at 25 meters per second, and after the collision is going at 18. So this is a positive number, and this is a positive number. The velocity of our truck has gone up. Some of the momentum that was originally in the car is now being transferred to the truck. There's a momentum transfer, but the total amount of momentum is the same before and after the collision. So if we wanted to find out what the v of the truck after the collision is, we can get out our calculator. And just to note here, the mass of the car is 1,200 kilograms. Mass of the truck is 9,000 kilograms. V of the car initial is 25 meters per second. V of the truck initial is 20 meters per second. And V of the car after the collision is 18 meters per second. So those are just numbers that we need that we can plug into our calculator. So we go here to our calculator, and I have VCI minus VCF, which is 25 minus 18, times the mass of the car, divide by the mass of the truck, Okay, that's a pretty small change in velocity. This velocity is added to the truck's initial velocity of 20. So after the collision, the truck is moving at 20.9 meters per second. Something to note here. Because of the vast difference in mass between the car and the truck, even though the car changed its speed dramatically, in this case by 7 meters per second, the truck didn't have such a change because it had much more mass associated with it. But this is a case of using conservation of momentum in some collision that's kind of between the two extremes. Okay. What's another thing that we could look at? I wanted to do a quick example of using some graphical techniques. So here in this problem, we have two cars. They collide at some intersection. Car A has a particular mass going from west to east, while car B of mass 1,500 kilograms is going from north to south at a certain speed. So looking at car A, we have a mass A and a velocity A that looks like this, giving us some momentum. Similarly, we've got car B going from north to south, like so. Now these are both momenta that we have before the collision, but we're told in the problem at this collision the two cars become linked together, become one new final mass, and my role as an expert witness is to determine after the collision how fast these things were going. So how fast was car A going before the collision? How fast were the enmeshed cars moving just after the collision? And this is going to tie a lot of interesting things together, because what we're going to see probably what happens after the collision, because we initially had an x component of momentum, final momentum is going to have some component to the right. Similarly, because we had some initial y component of momentum, our final momentum is going to have some y component of momentum as well. So these two are initial, and here is final. And if we wanted to put these two together, 65 degrees south of east, what we're essentially saying, after the collision, we're told this angle. This is the 65-degree angle in the problem, south of east. So here, this is MA, VA. Here, this is MB, VB. And here, this is M1 plus M2, V final. Graphically put together. And so we can use graphical techniques to figure out what's going on in the problem. So one thing we were asked to find, how fast were the enmeshed cars moving just after the collision, if we are told that it's moving at some particular angle. Now what I am told in the problem is not the speed of A, I'm told the speed of B, right? It's moving north to south at 15 meters per second, right? So I know VB, I know MB, this is A and B of course, I know those, and I'm asked to find this. I'm also told this angle. So using trigonometry, I don't need to know what VA is. I already know enough information. So looking at this, I see that this is the opposite side, and this is the hypotenuse. So I see the sine of the angle is MB VB over M1, or MA plus MB, V final. And so if what I'm trying to find is the final velocity, how fast were the enmeshed cars moving just after the collision, that is going to be MBVB over MA plus MB sine theta. And these are things that I know. So MA, just for the reference, is 2,000 kilograms. MB is 1,500 kilograms. And VB is 15 meters per second. So I can get out my calculator. MA plus MB is 2,000 plus 1,500 times the sine of 65 degrees is equal to this. That goes in the denominator, times mass of B times V of B. So we see that after the collision, it's moving at 7.09 meters per second. So even though we didn't know what the velocity of A was before the collision, because of the angle that it's leaving, we can actually find out some more information about the problem. So this is the final velocity, right? Going back to the text of our problem, how fast was car A going before the collision? We can find that now because we know the momentum before the collision and we know the momentum after the collision. These different relationships are still something that holds. So because I know the length of this side, because I know V final and the two masses, and I know the length of this side, stuff that was given to me in the problem, I can find the length of this side also, right? So what's the best way to handle this? Let's do this. If we were to do the tangent of theta, that's equal to MB VB, the opposite over adjacent, MA VA, and we know theta already, so if we wanted to, we can rearrange terms here to find VA. And maybe this is not the way it is proposed to be calculated in the problem, because there's lots of things you can do with trigonometry. You could do Pythagorean theorem stuff, whatever you want. But this is still a perfectly valid way of finding out what the initial velocity is needed to get this angle after the collision. So let's go back to our calculator. Let's do the denominator first. So mass of A, which is 2,000, times the tangent of 65 degrees. Put that in the denominator, times the mass of B, which is 1,500 kilograms, times the initial speed of B, which was 15. So this is 5.24. So casually looking at this, I see that this angle right here is very steep. 65 degrees is pretty steep. This is probably pictorially just about right. This side is pretty long. This side is pretty short. So having a larger mass, lower velocity, but still a smaller momentum is certainly representative pictorially here. You know, if the mass of MA had been a little bit less, this velocity would have been a little bit larger, as we see from this expression. But as far as pictorially speaking, these things sort of make a little bit of sense. And I just used graphical techniques here. There are algebraic techniques that I could have used as well. So we had an x component of momentum, that's the x component of momentum over here. Y component of momentum, that's the y component of momentum over here. I could have set up an x equation and a y equation, solve that system of equations to find out what's finally going on. The graphical techniques are just as well. That's what conservation of momentum means. What I'd like to spend the rest of our time with is looking at two cases where we use conservation of momentum leading to other things. Because very often, conservation of momentum goes with some other topic. And we can look again at another perfectly inelastic collision. Let's say we had a block of mass m2 that is hit by some other mass, m1, moving at velocity v1 before a collision. After the collision, this m1 and m2 are going to become one object. Perfectly inelastic collision. And after the collision, the block is going to slide. Block with the other mass is going to slide some distance d. And I would like to find out how far it slides given how much momentum I put into the problem. Now these are the two things that are colliding, m1 and m2. And m2 is initially at rest. So the initial momentum in the problem is m1 v1. After the collision, the two objects become one object, and the composite new object is going to move off at some final velocity v. And if we wanted to, we could find out what that final velocity is. V final is going to be m1 over m1 plus m2 v1. And so because m1 plus m2 is bigger than m1, this new composite object is going to be going at some slower speed. But this isn't all of the problem. After the collision, something else happens. Now we have this new composite object that has some kinetic energy. And it's going to slide until it stops by having frictional work done on it. Mu m1 plus m2, the mass of the new composite object. G, the weight of the composite object. This is the normal force of this new composite object being applied by the table, times some distance d. So this is energy lost to frictional work. This was kinetic energy that the composite object had after the collision. And so if we wanted to find d, we actually could. And before we get there, let's do a little bit of solving of things first, because inside this expression for conservation of energy, we have this v final. something that we've already calculated. So we see that 1/2 m1 plus m2 v final squared is m1 squared over m1 plus m2 squared v1 squared is equal to mu m1 plus m2 gd. So one of these m1 plus m2's cancels with this one, and solving algebraically, d is going to be m1 squared v1 squared over 2 mu m1 plus m2 squared g. So let's look at a couple of things here associated with units. First, m1 plus m2 squared and m1 squared have the same units. Mu is dimensionless. So we've got the units of v squared divided by g. V squared is meters squared per second squared divided by meters per second squared, which means we have meters squared divided by meters, or a meter. This has the right kind of units. Now, what are some other things that we see associated with this? If I was to throw the clay ball quicker, the final composite object is going to slide further because of this v1. If m2 is very massive compared to m1, m1 divided by m1 plus m2 is then going to be a small number. It's not going to slide very far. If I throw a little bit of Play-Doh at a bowling ball or something, it's not going to slide very far. If we have no coefficient of friction, all of a sudden this d turns into infinity. So if we didn't have friction, it would slide for forever. That kind of makes sense. But the bigger that coefficient of friction is, the less distance it actually slides. So this has a lot of the behaviors that you might expect to come in here. But what we had is a collision that happens, and then something happens after. In this case, it's conservation of energy. Is that always going to be the case? Not necessarily. Let's look at one last problem before I end this video, and that's the problem that's shown here. So let's say we have a bullet of mass m fired into a block of slightly different mass sitting at the edge of a table. Now, looking at this, the block is going to land some distance d from the bottom of the table, and we're supposed to find the initial speed of the bullet. So there's two parts of the problem that happen here. One part is the collision. Every time we have a collision, we have to do conservation of momentum. But after the collision, other stuff happens with some composite object. So if I was looking at this problem, I see that before the collision, we have little m, the mass of the bullet, moving at some velocity v. That's something that we're going to have to find later, but let's call it velocity of the bullet. Okay. Initially, the big block is not moving, but after the collision, mass of the bullet plus mass of the block is going to lead to a final velocity of the block, right? And if we wanted to find that final velocity, mass of the bullet over mass of the bullet plus mass of the block, v of the bullet, the thing that we're trying to find. But so we've got some final velocity that's going to happen, right? Now what's going to happen afterwards is a conservation, or is a kinematics problem, right? So we see that, for example, in the x direction, d is going to be v final times time, because there's no acceleration in the x problem. And let's just make one step back. X final equals x initial plus v initial xt plus 1/2 ax t squared. But x final is equal to d, x initial is equal to 0, v initial in the x direction is vf, and there's no acceleration. So that's where I got that equation. D is equal to vf t. But we also have y final equals y initial plus v initial in the yt plus 1/2 a in the y t squared. This is 0. This is h, the height of the table. We had no y component of initial velocity, but it is falling under the influence of gravity. So if we wanted to find, we were maybe given what d was, right? And so we didn't know what the time was, but we wanted to find out what Vf is. So maybe I could use this equation to find the time that the block was in the air, right? This is the time that the block is in the air before it hits the ground. I can take this time and plug over here and see that Vf is equal to d over that time. I just flipped this thing to do what we were trying to do. This is what V final is. Okay. Well, this V final and this V final, I want to find out what the final speed of the bullet is, right? So what we see is that m over m plus, this is supposed to be big M, velocity of the bullet is equal to d g over 2h, or that the speed of the bullet initially is given here. Now this particular problem didn't have numbers associated with it. That's fine. I don't know who's calling me all day today here. But now we can find a couple of things that are associated with this. So if we had a bullet that was traveling, so here we look at a couple of different behaviors. If the thing ends up very far from the edge of the table, d is large, our bullet must have been moving larger as well. The faster the bullet goes, the bigger d is going to be. If h starts to get smaller and smaller and smaller, the velocity of the bullet is going to be required to be much larger because of some given value of d. It doesn't have as much time to fall if h starts to get smaller. And if h starts to get bigger, it has a longer time to fall. A velocity of a bullet does not need to be quite as large to get a certain value of d. We also see this ratio of little m plus big M over little m. If the block is very, very massive, this could actually be a substantially very large number. So even though the block bullet composite object isn't moving typically particularly fast after the collision, man, the bullet can really have a lot of velocity that's associated with it. Now this is very similar to the last problem we looked at. In the last problem we had a collision that led into a conservation of energy problem. This is a collision that leads into a kinematics problem. And it's possible to even have a force problem after the fact, or a different kind of energetic problem after the fact. But this is sort of to give you some flavor of how to do some kinds of collisions. Now I realize now that all the collisions that I had prepared were perfectly inelastic collisions, but the same is true. The process and the techniques are also going to hold for perfectly elastic collisions and everything in between. I guess my car and moving van was somewhere in between. That's fine. But I do have examples of perfectly elastic collisions in the Canvas page as well, and maybe this is a good place to stop for our discussion of collisions. We do still have one more video in this unit that's associated with center of mass and the famous rocket problem.